induced EMF in an alternator or synchronous generator. The topics to be covered today are armature winding of an alternator, the winding factors of an alternator, distribution factor, pitch factor, the EMF equation, and the effect of harmonics on the winding factors. Generation of three-phase EMF in the alternator. Three equal voltages, that is by magnitude and of same frequency having a phase difference of 120 degrees, is produced by having the three identical windings displaced by 120 degrees electrical in the stator of the synchronous generator. Now three identical coils A1, A2, B1, B2 and C1, C2 are placed on this stationary armature. When the magnetic field is rotated in the anti-clockwise direction at the speed of omega radians per second, then the coils are kept stationary and an EMF will be induced in each winding of the phase. The three EMFs are of the same magnitude and frequency, but they are displaced by 120 degrees each from one another. These can be represented by the equation as EM is equal to sin omega t, EB will be equal to sin omega t minus 120 and EC can be written as sin omega t minus 240 or sin omega t plus 120. So this is the waveform representation of the given waveform and this is your phasor representation of the three waveforms. Now what are the harmonics in the voltage waveform? The harmonics in the output voltage waveform are developed due to non-sinusoidal waveform of the field flux. These are developed due to the variation in the reluctance of the air gap because of the slotting of the stator core. Now how can we do the suppression of the harmonics? The harmonics can be suppressed or eliminated by well distributed armature windings, using short pitched windings instead of full pitch winding, by skewing the poles by one slot pitch and by using fractional slot winding, and by using the larger air gap length to increase the reluctance of the given machine. Now the armature winding of an alternator, you can see over here we have taken a simple winding of a double layer. So A1, A2 and A3, A4 are placed in two slots and all these four windings are connected in series. So for consideration over here, it is a two pole, three phase, double layer, full pitch distributed winding taken into consideration. 12 slots, each slot containing two coil sides will be devoted for this. A1, A3 or A2, A4 constitute a phase spread of 60 degrees electrical. Each coil has a span of full pole pitch, that is 180 degree electrical. 12 total coils for, and each phase has got 4 coils. So the 4 coils in each phase are connected in series, so the voltage will be added. The 3 phases can be connected to form the star or the delta connection. Now what are the winding factors of the alternator which has to be taken into consideration? The armature windings of an alternator is distributed over the entire armature. The distributed winding produces nearly a sine waveform and the heating is more uniform. The coils of the armature winding are not the full pitch coil, but it's the fractional pitch which is being used, and the two sides of a coil are not at the corresponding points under adjacent poles. Okay, that means it is not a full pitch. If it is directly under the adjacent poles, it will be a full pitch, that is 180 degrees separation. The fractional pitched armature winding requires less copper per coil and at the same time the waveform of the output voltage will be improved. What are the different winding factors of the alternator which has to be taken into consideration? The armature winding is distributed over the entire armature and that distribution produces almost a sine wave and the heating will be more uniform. The coils of the armature winding won't be full pitched, and that means the two coils of a coil are not exactly under the adjacent poles. The fractional pitched armature windings require less copper per coil and at the same time waveform of the output voltage is also improved. The distribution and the pitching of the coils affect the voltages induced in the coil and therefore we'll discuss these two winding factors before discussing the actual EMF being induced in the alternator. That is, the distribution factor is called the breadth factor, and the pitch factor is also known as the chord factor. Now, what is a distribution factor? How do we calculate it? For this type of winding, the EMF generated per phase is equal to the arithmetic sum of the individual coil EMFs in that phase. But if the coils are distributed over several slots, in that case the total EMF of the coils won't be in the it has to be the phasor difference for the all the waveforms to be added together. It won't be the arithmetic sum. Now we'll discuss the distribution factor in the synchronous generator. When the winding is distributed, the EMF generator per phase is not equal to the arithmetic sum of the individual coil EMFs being added, but it will be the phasor sum of the EMF generated per coil. So if the coils are distributed, there will be several slots in the space, and the EMF in the coils are not in phase but are displaced by a slot angle of alpha. Therefore, the angular displacement in electrical degrees between the adjacent coil is called the slot angle. The EMF per phase will be the phasor sum of the coil EMFs. The distribution factor is defined as, therefore, the EMF with distributed winding divided by the EMF with the concentrated winding, because in the concentrated winding the EMFs will be the algebraic sum, and in the distributed winding it will be the phasor sum. So it can be also defined in terms of the phasor sum of the coil EMFs per phase divided by the arithmetic sum of the coil EMFs per phase. Here the numerator is less than the denominator, so KD will be always less than 1. The distribution factor will be always less than 1. So to derive the expression of the distribution factor, here we have considered 3 slots for the distribution of the single phase per pole. So the expression for the KD will be alpha is the slot angle, and the slot angle is equal to 180 degrees electrical divided by number of slots per pole, and N is the slots per pole per phase. Therefore, the distribution factor for the phasor diagram, we have considered the N is equal to, that is slots per pole per phase is equal to 3, and the 3 coil phasors are AB, BC and CD. Each is a chord of a circle with center O and subtends an angle of alpha at O. The phasor sum of these coils will subtend an angle of, total angle will be N alpha, that is we have taken 3 coils, so it will be 3 alpha, and for each from each of the coil we will draw a perpendicular bisector on OX and OY. OX is the perpendicular bisector of AD and OY is the perpendicular bisector of AB. Therefore, KD will be given as AD, which is the total EMF being generated by the 3 coils, divided by the arithmetic sum will be AB plus BC plus CD, which can be given as N into AB. So, generalizing the expression, you can get it as OA into X N sine N alpha by 2 divided by N OA X sine alpha by 2. So KD will be equal to sine N alpha by 2 divided by N sine alpha by 2, where N alpha is the phase spread of the given winding. Now just a brief idea to how the distribution factor varies with the slots per pole per phase. So if the number of slots per pole is 3, 6, 9, 12, 15, 18 and 24, then the slots per pole per phase you have to divide it by 3 because we are generating 3 phase voltages. So divided by 3, you will get the value of the N. Alpha will be calculated accordingly. So the phase spread will be as 60, 30, 20. And the distribution factor, you can see it will go on reducing. But later on, when we distribute it for a large number of slots, in that case, the variation is not much. It is around 9.55, 56, 57 and all. So now we'll discuss about the pitch factor. A coil whose sides are separated by one pole pitch is called the full pitch coil. This we have already discussed about the full pitch and the fractional pitch in the armature winding discussion. When a full pitch coil is used, the EMF induced in two coil sides in a phase with each other, and the resultant EMF is the arithmetic sum of the individual EMFs. The waveform of the resultant EMF can be improved by making the coil pitch less than the pole pitch. Hence, the name is given as the short pitch coil. The practice is possible with the double layer type of winding, and the EMF induced in a short pitch coil is less than that of a full pitch coil. The factor by which the EMF per coil is reduced is called the pitch factor, or it is denoted by Kp. Kp is defined by EMF induced in the short pitch coil divided by the EMF induced in the full pitch coil. That is, it is the ratio of the EMF induced in the short pitch to the EMF induced in the full pitch coil. So now here we can do the derivation. We can find out its expression. What is the expression for the pitch factor? So for that we have taken as the angle between the two coil slots. That is, we are considering a coil AB with a short pitch by an angle of beta. That is, one slot is less than the full pitch. The EMF generated in the coil sides AB differ by an angle beta, and it is represented by EA and EB respectively. So just it will be the resultant EMF will be the phasor sum of EA and EB, which can be mathematically given as ER is equal to 2EA cos beta by 2, because EA will be equal to EB. So as per the expression before, we will substitute the values and we can get as Kp is equal to cos beta by 2. So for a full pitch winding, your Kp, the pitch factor will be equal to 1, and for a short pitch winding, Kp will be less than 1. The pitch factor will be less than 1. So beta is always, because beta is always an integral multiple of slot angle. Now here we can see an example over here. We have taken few examples. That is, we have considered a coil of 36 stator slots, 4 poles, and the coil span is only 1 to 8. So actually for 180 degrees complete full pole pitch, it should be from 1 to 10, because the coil span, how much it is shorting fall off, that is 2 by 9 into 180, that is beta will be equal to 40 degrees, because it is falling short of 2 pole pitch, 2 slots, while the total distribution had to be in 9 slots. So the winding has to go from 1 to 10. Therefore, once you calculate the beta, you can calculate the pitch factor as cos of beta by 2, that comes to as 0.94. Now for the second case, where you have to take 72 stator slots, 6 poles, and coil span will be from 1 to 10, which is being used. So over here, what should be the coil span? The coil span should be from 1 to 13, because per slot, per phase will be, per pole will be 12. 72 divided by 6, that is 12. So slots per pole will be equal to 12. So instead of 1 to 13, the coil is now short pitched by 1 to 10. Hence the Kp will be equal to 3 by 12 into 180, that comes to as 45 degrees. So cos 45 by 2, that is 0.924. So now the actual derivation of the equation, EMF equation, that is the EMF produced by an alternator. Now we'll consider Z as the total number of conductors per coil sides in series per phase. Phi is the flux per pole. P is the total number of rotor poles, and N is the rotor speed in RPM. So for one revolution, that is N is the R in RPM, so 60 by N will be the time taken by the to complete one revolution. So each stator conductor cuts the total flux as P into the flux per pole. The total number of poles into the flux per pole will be the total flux. So the total flux cut is P into phi, and for one complete revolution the time taken is 60 by N. So we can say that d phi is equal to P phi and dt is equal to 60 by N. So the average EMF induced in one stator conductor will be d phi by dt as per the electromagnetic law of as per law of electromagnetic induction. So substitute the values, you will get as P phi N by 60 volts. Now this is the average EMF. So if the Z are the total number of conductors in series per phase, then average EMF per phase will be P phi N by 60 into Z. Now N will be substituted as the synchronous speed, that is 120 F by P. So you will get the average EMF per phase equal to 2 phi Z into F, where F is the frequency of the EMF being generated. So the RMS value will be average value into the form factor, that is 1.11 for a sine wave. So the RMS value will be 2.22 phi ZF. Now number of turns is equal to total number of conductors divided by 2. So you just substitute it in the number of turns, will get the RMS value of EMF per phase equal to 4.44 phi FT. So considering the distribution factor and the pitch factor, because both are less than 1, distribution factor as well as the pitch factor, so the RMS value of the EMF per phase becomes as 4.44 kd kp phi f into total number of turns T. Now what is the effect of harmonics on pitch and distribution factors? If a short pitch angle or recording angle is beta for the fundamental flux wave, then its value for different harmonics will be third harmonic 3 beta, for fifth harmonic it will be 5 beta, and so on for the higher order of harmonics. So the pitch factor will have Kp is equal to cos beta by 2 for fundamental, cos 3 beta by 2 for third harmonic, and cos 5 beta by 2 for the fifth harmonic. Similarly, the distribution factor is also different for different harmonics. Its value will be given as, for fundamental, Kd we had defined as sin n alpha by 2 divided by n sin alpha by 2. So substituting the value as, for third harmonics, you will get Kd is equal to sin 3 n alpha by 2 divided by n sin 3 alpha by 2, and for fifth harmonics it will be sin 5 n alpha by 2 divided by n sin 5 alpha by 2. So today we have discussed about the armature winding of an alternator, the winding factors of an alternator, that is the distribution factor and the pitch factor, then the actual EMF being generated in the alternator, and the effect of harmonics of the winding factors. Thank you.